The next portion of our Chemistry 20 chemical bonding unit is looking at the types of bonds that can exist in different compounds. So we're going to start with the concept of electronegativity because in a big part, electronegativity is what determines the type of bond that will form between two elements. So electronegativity is the general ability of an atom to attract or pull electrons. And we can assign a rating or a number, and this is based on the Pauling scale, that we can determine how strong of an ability an element may have to pull electrons. So we assign these numbers, and generally it's from a 0 to a 4 scale. And we see a few general periodic trends. So we notice with our periodic table, our electronegativity increases as we go up the periodic table and as we move right on the periodic table. So we'll notice that our lowest electronegativity is francium with a 0.7 electronegativity. And if I zoom in, it's a little bit blurry. And as we go up and to the left, we notice that our highest electronegativity is fluorine with an electronegativity of 4.0. So we have this scale, and it's a relative scale of our elements to pull electrons. Now, the higher the electronegativity, okay, so the electronegativity of 4, for example, means that there's a greater ability to pull. Okay, the lesser the electronegativity, the weaker the pull. Now, I almost like to think of this as a competition between these elements as almost like a tug-of-war competition. We're all pulling for the rope, or we're all pulling for the electrons, but one side will be stronger in general. Okay, so if we look at the first type of bonds, it is called a covalent bond. Now we see covalent bonds generally in molecular compounds. So we see it between two nonmetal atoms, which is the equivalent of saying that we see this in, I need to make that a little bit smaller, molecular compounds. So it's the simultaneous attraction of two nuclei for a shared pair of bonding electrons. Now, that's a little bit wordy, but essentially, there's two atoms that are pulling electrons, and it would be this tug-of-war example at the bottom, where we're both pulling on the electrons, and one side might be a little bit stronger, a little bit winning of that tug-of-war competition, but no one fully wins. There's a little bit of sort of back and forth action, you could think of it as, and essentially one element might be a little bit stronger, but the other element doesn't give up. It doesn't fully release that electron. Okay, now we generally see this with two elements with high electronegativities. So if we jump back to our periodic table, and I'm going to jump to your periodic table that you will have, we see, let's see it like this. Okay, so we see that these elements, sort of as our nonmetals, have high electronegativities. Now, on your periodic table, you'll notice that electronegativity is this value in that sort of top or middle section left side, and it's above our element symbol. And we see that with our nonmetals, with our covalent bonds, we have relatively high electronegativities. Now that's relative compared to, let's say, some of our other metals. We notice 0.9 is significantly smaller than something like 2.6. So we have these electrons being shared in between these atoms. So, if we jump back to our lesson, okay, so we have electron sharing. Again, it's covalent. We have a sharing of electrons, and that sharing can be equal or unequal. So we can have equal sharing or an equal tug-of-war where we have the exact equal strength on both sides, Or we can have unequal sharing where one side is a little bit more greedy or a little bit more strong. They can pull a little bit harder than the other side, which would result in unequal sharing of electrons. Now, we can also have this thing called an ionic bond. And an ionic bond is an attraction between a cation and an anion. Again, we see this in ionic compounds. Okay, and the net charge must equal 0. So this is when we have charge balancing. For example, if we have a charge of iron 3 and oxygen 2-, we have to make sure we have 2 irons and 3 oxygens to have that net charge being 0. Okay, we also form a 3-dimensional crystal lattice, and the 2 elements that form it, one has a significantly higher electronegativity and it steals the electrons. The other electronegativity is weak enough that it just gives up. It doesn't even participate in the tug of war. The other element just steals that rope, runs with it, and runs away. Okay, so this is called an ionic bond. We have a full transfer of electrons. Now I might jot that down, transfer of electrons. Now this makes sense because when we have an ionic bond formed, we result in anions and cations. So when we get anions and cations as a result, if we have something that has a positive charge, let's go with calcium 2 positive, that means that it lost 2 electrons. And if we have oxygen 2-, this means that we gained 2 electrons. Well, if I have calcium oxide, the 2 electrons that were lost from calcium were given or gained by oxygen. So this does make sense that we have a greater ability to pull electrons, and for this example, oxygen has so much greater of an ability to pull electrons, it's so much stronger than our calcium, that it completely steals those electrons. Okay, so that is something to keep in mind when we're talking about covalent versus ionic bonds. Now this is a way that I like to remember what an ionic bond is, and it's a play on words with our famous James Bond. And this, he says, my name is Bond, James Bond, shaken, not stirred, right? That's kind of the iconic saying. And this is the name's Bond, ionic bond, taken, not shared. So that's an easy way to also remember what an ionic bond. They're talking about the electrons. Okay, electrons are taken, not shared. So that's a good way to remember it. I like that one, and it seems to stick for a lot of students as well. So we also have this thing called metallic bonding. Now, metallic bonding isn't so much of a sharing or stealing of electrons, but instead the electrons that we have in a metallic bond seems to be acting as a glue. So if we have atoms with low electronegativities, which is our metal elements, okay, the atoms share valence electrons, but no chemical reaction takes place. There's no transfer of electrons or no real sharing of electrons, but they have these electrons that act as glue that surround our positive atoms, so this nucleus of our atoms, and essentially the electrons just disperse around those positive nuclei, and they just act as glue holding that whole structure together. So if we have multiple atoms of, let's say, copper or something like that, we have the electrons that will surround those atoms or the nuclei of the atoms, and they will basically collide or share those electrons, not in the same sense as covalent bonds share, but they'll sort of act as a glue, a sticky glue that will surround those nuclei to hold the whole structure together. Now, a big portion of this unit is looking at molecular compounds. So we are going to look a little bit more at molecular formulas and what it means for our chemical bonding. So molecular substances are described in terms of their chemical bond. Okay, we have a chemical bond that is covalent. Okay, that is very important. That word co, meaning share. They're sharing electrons. Okay, so we have molecular compounds that can be of more than one non-metal in a compound. However, we can also have these things called molecular elements. Now we have diatomic or polyatomic atoms, and they have covalent bonds between the atoms. So we would have something like our molecular elements. Let's look at our diatomic elements first. We have hydrogen, we have nitrogen, oxygen, fluorine, chlorine, bromine, basically any of the halogens, iodine, and I do believe like that as well. So we have our molecular elements. Basically, it's HNO and our halogens that are our diatomics. As our polyatomics, we have P4, which is phosphorus, and we have S8, which is sulfur. Now, these are the elements found in their natural state. In nature, we do not find oxygen as a single atom. We always find it as diatomic. Same with any of the other diatomic elements listed. And in nature also, we find sulfur, and we don't find just a single sulfur atom. We find 8 sulfur atoms bonded together. So if we think about our Lewis structures, we no longer have a Lewis structure that looks like this. I'm going to give you the example of chlorine. We know that chlorine has 7 valence electrons if I look at my periodic table. And because it is chlorine gas, and we know that chlorine has, I guess I should do this properly, 1, 2, 3, 4, 5, 6, 7. So we have 7 electrons. And when we take a look at what Cl2 looks like, we have 1, 2, 3, 4, 5, 6, 7. So we have this bond in the middle where we have shared electrons. Now, part of the reason is based on the electronegativity. Part of the reason is based on the fact that if we have 2 elements with 7 electrons, we can make both happy if we pair them up, which is a good reason as to why we have all of these diatomic elements. Okay, so this is what our Lewis structure would look like. Now, again, this is still a covalent bond. But because I have 2 elements with identical electronegativities, this covalent bond is where electrons are shared completely equally. There's no element that's stronger, that's pulling harder. There's no element that's going to steal electrons. It's just a perfectly shared covalent bond. So molecular formulas are the actual composition of an atom. Okay, it's not the simplest ratio. So when we are dealing with ionic compounds, we just simply put the simplest ratio down. For example, if we had manganese, so with ionic, I'm just going to write this down so we don't get confused, ionic compounds. We have an example with, if we have manganese 4 plus and oxygen 2 minus, we write this down as MnO2. We use our simplest ratio formula, so we use our simplest whole numbers to write this down. Now, with molecular formulas, we will actually write the physical composition of those atoms and the order of the atoms instead of simplifying our ratio. So that is an important thing to note. That's with molecular formulas. Okay, we also need to know that covalent bonds are strong directional force. Now, essentially, they're only a directional force if there is one element that has a higher electronegativity. Like we saw in the previous slide there, if we have chlorine and chlorine with identical electronegativities, there's no directional force. It's just a strong bond between the molecule. Okay? Now, the purpose of a molecular formula is to show, again, this arrangement of atoms. We can show how the atoms are actually bonded in physical space. Now, we also have to consider a few other things. We can have double bonds, which we've seen. We've seen double bonds with our Lewis diagrams. Anywhere where we have 2 pairs of electrons between 2 atoms, which is when we have to move those electrons in our Lewis diagrams to make a full octet, right? We want every element to be happy, and so when we have to move those pairs of electrons, we make a happy element. Now, because we move those electrons, that gives us what we call a double bond. And a triple bond is a sharing of 3 pairs. So if we had to move another pair of electrons into a bond, or turn a pair of lone pairs into bonding pair electrons, we will get a triple bond. Okay? Now, again, we've talked about bonding capacity. This is just a review. And essentially, it's the maximum number of single covalent bonds that an atom can form. So that's the number of bonding electrons, which is equal to your bonding capacity. So if we look at something like carbon, carbon has 4 valence electrons. This is bonding capacity equals 4. If we look at something like oxygen, we have 1, 2, 3, 4, 5, 6 valence electrons, which means that our bonding capacity equals 2. Notice your bonding capacity is dependent on the number of bonding electrons that are present on that atom. Okay, now we've already talked about how bonding capacity is important when we look at our Lewis diagrams. So bonding capacity is also important in terms of molecular compounds and forming bonds, because I know that oxygen can only form 2 bonds, where carbon can form 4 bonds. Okay, if I look at something like chlorine with a bonding capacity of 1, that can only create a single bond. So that is an important thing to note when we are going through our molecular compounds and getting an understanding of these molecular compounds. So one more thing to take note of is that there's sort of a common way to notate molecular formulas, empirical formulas, and we can look at molecular and empirical formulas as well as Lewis formulas and a few others for every single compound or element that we look at. So if we look at a couple examples, I'm going to show you 2 examples. I'm going to start with our empirical formula of, let's go with water. Now, water is H2O. And what H2O means is that there's 2 hydrogens for every single oxygen present. Now, that is our empirical formula because it's a 2-to-1 ratio. It is the simplest whole number ratio. Now, our molecular formula is exactly the same. We still have 2 hydrogens because this actually shows that we only have 1 oxygen for every 2 hydrogens. Now that is not only your empirical formula, but that's actually just your molecular formula as well. Now our Lewis formula shows how electrons are shared. So if we have our oxygen, okay, we have oxygen with 6 electrons. Each hydrogen contains 1 electron, giving us a total of 8 electrons. Now if I draw this out like this, we have our hydrogen and our hydrogen, and we have our electrons in between there, 1, 2, 3, 4. Hydrogens are happy with 2, remember? So then these electrons then go on our oxygen. So the way that this Lewis diagram is drawn looks like this. We have 8 total electrons in it, 2 bonding pairs, and 2 lone pairs. Okay, so we have a Lewis formula. Now I can continue to take a look at my example with water, and I have a structural formula, and my structural formula shows the number of atoms bonded as well as the type of covalent bond, which means single or double or triple bonds. Now if I draw this out again, I would just simply draw this as water, and it has an oxygen and a hydrogen on 2 separate bonds. Now notice I've replaced my bonds, or my dots, as bonding electrons as bonds. Now sometimes you may see that there's 2 extra electrons here and here to show the lone pairs, but I don't like to include those in structural formulas because that's kind of a blend between a structural formula and a Lewis formula. Now the stereochemical formula is a 3-dimensional representation of the molecular shape. So if I look at an example such as water again, this example is actually the same as our structural formula because our water molecule exists sort of what you can think as 2 dimensions. And we think of the 3 dimensions as x, y, and z. So when we think of that, we have x and y, which is sort of our regular 2 planes that we have, x and y. And then z is this plane that goes through our center of our x and y, and that would be a plane that's sort of coming out of the page towards you, or out of your computer screen, whatever you might be watching this video on. So when we have our our water molecule, we have our X and our Y. Now we have no component that's coming out of the page towards you, okay, which would be sort of through, if you can picture putting a pencil up to the edge of the page and that pencil coming out towards you from this oxygen atom, then that would be your Z. But because we don't have that, we only have an X and a Y. So our structural formula is our actual stereochemical formula because we only need to draw it in 2 dimensions. Now, if I go back and show you another example, I will show you an example of methane. Now, methane is CH4. CH4. Okay, now our molecular formula again here matches our empirical formula because our molecular formula tells us that or our empirical says that there's 4 hydrogens for every 1 carbon. Okay, now in our molecular formula, we also see that we have 1 carbon, which means we have 4 hydrogens. We don't have any more than 1 carbon in our single molecule. So when I go to draw this out, I see that carbon is our central atom, and I have 4 hydrogens. I place those guys around my carbon. My carbon has 4 electrons. Each hydrogen has a single electron, making a total of 8. So when I draw those in, it looks something like that. Okay, so there's my Lewis formula of my methane. Now if I go to draw my structural formula, it looks something like this. I have my carbon in the middle. I have my 4 hydrogens. Okay, now when it comes to my stereochemical formula, this is where it differs a little bit from water. Since we know our bond angles of our, which you'll learn in a little bit here, we know that these angles are just a little bit greater than a 90-degree angle, which means that because of that, when we have it represented in a 3-dimensional shape, we actually have a carbon in the center, and we have, again, an X and a Y component. So I'm going to label that as X and Y because, again, that's sort of the flat, oops, that's the wrong letter, Y and X. And then what you need to picture in your mind is that we also have an element that is coming towards you, okay, and we draw that with a sort of a little sliver of a pie or a little triangle, and we represent that as an H. Okay, now this is considered the Z. Now, on that same Z, if you picture that now, if this is a pencil maybe coming out towards you, this is the eraser tip, but we also have to draw the tip of the pencil, which is now pointing into the page, and we like to draw that as sort of a dashed line. Okay, now our dashed line is our hydrogen. Now this is still part of our Z component. It's just the pizza sliver here, or the pie sliver, is the tip of your pen, or the eraser bit of your pencil, and this is the tip of your pencil. Now, because we're drawing a 3-dimensional drawing on a 2-dimensional page, we have to represent that with symbols. Now the dashed line is going away, the pizza symbol is coming towards you, so we can represent that in 3 dimensions. Notice how our stereochemical formula is different than our structural formula when we have to draw the 3rd dimension. Now, I'm going to just jump back here really quick, and I'm going to give you an example where we see an empirical formula and a molecular formula being different. I'm going to give you the example of benzene, and I'm just going to do this in a slightly different color because I'm not going to go through all of the examples with benzene. Okay, benzene, our molecular formula for benzene is C6H6. Now, because I have 1 carbon and 1 hydrogen as my lowest, simplest formula, then my empirical formula for benzene would be CH, which doesn't really tell us a lot about the molecule. It just tells us that for every single carbon, there's 1 hydrogen, but it doesn't tell us how many carbons there are in existence and how many hydrogens there are in existence. That is why our molecular formula here often gives us a great deal more information about what is going on in that chemical compound. Now, I would like you to watch the Khan Academy video after this, and he'll go through this concept again of looking at our empirical, molecular, and structural formulas. So that will give you a better idea of this benzene example too, to see how our empirical and molecular formulas do differ. So now that we've taken a look at the types of formulas and the types of bonds that we have, remember the types of bonds is ionic and covalent, and in our molecular formulas we can have a variety of different ways of representing the same molecule. Now, that is an important thing to remember as we go forward in this unit. And now that we know about electronegativity and how electrons are either shared or taken in different bonds, remember covalent means sharing of electrons, ionic is stealing of electrons, we can start to determine some more concepts regarding our molecular compounds, and we can come back to our ionic compounds towards the end of the unit. So as you go through, like I mentioned, I would like you to watch that Khan Academy video next, and good luck!